let us consider one more example. Using the rule for periodic functions, find Laplace transforms of two functions A a pulse train like this, like that it goes 0, t upon 2, t, 3t upon 2, 2t, 5t upon 2, etc., with an unit amplitude. B, a single pulse of a sinusoid 0 to t upon t naught upon 2, where omega naught equals 2 pi upon t naught. So, this will be, suppose this is 1, this is sin omega naught t in the interval from 0 to t naught upon 2. So, I can write this as u t minus u t minus t naught upon 2. This is something which we already discussed earlier, but we would like to arrive at the result in a different fashion. Now, take this. We have a pulse train here. So, if we know the Laplace transform of one single pulse, we can find out the Laplace transform of the pulse train, because it is a periodic repetition of the same event. Whatever is happening from 0 to t, capital T is repeating itself. So, if you want to find the Laplace transform of just this portion, we know that this is equal to u of t minus u of t minus t upon 2. This function is simply a step function minus a delayed step function starting at small t equals t upon 2. Therefore, the Laplace transform of this is 1 over s. This the Laplace transform of this is 1 over s. The Laplace transform of this is the same 1 over s, but multiplied by e to the power of minus t upon 2 times s. That is the Laplace transform of this. Now, all we are having is the same pulse is repeating itself identically every capital T seconds. Therefore, this is a periodic phenomena, and we found out the Laplace transform of the phenomenon in one period. So, the entire periodic function will be obtained by 1 over s 1 minus e to the power of minus t by 2 s, the basic function divided by 1 minus e to the power of minus t s, according to the rule that we had earlier derived for a periodic case. So, the answer is 1 over s. You can put it in this form if you wish, or 1 over s times 1 over 1 plus e to the power of minus t by 2 s, because this is a factor here. So, that is the answer for this the Laplace transform of this periodic pulse train. Now, when you go to B, we have derived this in a different fashion, but now I would like to derive it using the property of the periodic function. Suppose I call this g of t. Then let me say that this has a Laplace transform g of s. Now, suppose I extend this like this. I complete the sine function for one complete period. If this had a Laplace transform g of s, what would be the Laplace transform of this? This portion would have the Laplace transform g of s. Suppose this portion had been flipped over like this. This had been flipped over like this. Its Laplace transform would have been g of s multiplied by e to the power of minus t naught by 2 s, because the same thing is delayed by t naught by 2 seconds. So, the Laplace transform of a simple a loop like this would have been g of s times e to the power of minus t naught upon 2 s. But now, instead of this, we are having a negative going thing. Therefore, this will be plus minus g of s times e to the power of minus t naught by 2 times s, or in other words the Laplace transform of this one period of this sine wave would have been g of s times 1 minus e to the power of minus t naught by 2 times s. That would have been that would be Laplace transform of this in terms of the Laplace transform of this. Now, suppose this sinusoid is repeated endlessly. So, that is a complete sin omega naught t u t repeating endlessly. Since we know the Laplace transform of one period, you can find out the Laplace transform of the entire periodic function by dividing this by one minus e to the power of minus t naught times s. This is the Laplace transform of this. But we know the Laplace transform of this. This is after all sin omega naught t u t. And we know the sin omega naught t u t has a Laplace transform omega naught over s squared plus omega naught squared. So, the Laplace transform of this, which was derived in terms of the Laplace transform of the single loop, must be equal to omega naught over s squared plus omega naught squared. Therefore, equating these two, we get the result that g of s equals omega naught over s squared plus omega naught squared multiplied by 1 minus e to the power of minus t naught s divided by 1 minus e to the power of minus t naught s upon 2, which is simply omega naught over s squared plus omega naught squared into 1 plus e to the power of minus t naught s upon 2, a result which we have already derived in the last lecture or so using a different property. What we did was, if we had a sine wave like this and another sine wave which is delayed by t naught of 2 seconds, if you added these two, you would produce this pulse. So, from this we arrived at the same result in a different way, but now we got the same result using the property of periodic functions. We had so far talked about the transformation in the forward direction, that is, given function of time, we are trying to find out the Laplace transforms. But in the solution of network transients, we also have occasion to have to find out the inverse Laplace transformation. Given f of s, we should like to find out what the f of t that corresponds to it is. This is called inverse Laplace transformation. Now, this inverse Laplace transformation can be approached from 2 points of view. One is to the what is called the partial fraction expansion, that is what we will discuss primarily. It also can be approached through the defining integral relation of f of t, getting f of t from f of s, the inverse transform integral relationship, which goes, as you remember, 1 over 2 pi j integral from c minus j infinity to c plus j infinity of f of s e to the power of s t ds. The second approach is little complicated, and it can be used only for when special occasions arise, but for ordinary purposes it is enough we know how to find the inverse Laplace transformation to the partial fraction expansion. So, let us consider the partial fraction expansion as the method of as the preferred method of finding out the inverse Laplace transformation. The approach that we take up here is somewhat analogous to what we do when we take up the integration of functions. You know, when we have to integrate something, the integrand is split up into components which are recognized to be the derivatives of some functions. So, once we recognize the derivatives, then the functions whose derivatives they are we know, and then sum of all those functions will be the integral of the various derivative functions that we know. More or less the same approach we take up here also. In other words, normally the f of s that we have to deal with is a rational function. So, we split up this rational function as a sum of small elementary functions which are Laplace transforms of known time functions. So, if you do that, then the sum of all these elementary functions will have an inverse Laplace transform, which is the sum of the corresponding time functions which we recognize as the mates of the elementary functions. That is what we do. So, split up f of s, the philosophy is split up f of s as the sum of elementary terms which are Laplace transforms of known time functions. This is the philosophy. So, let me illustrate this. For the particular, let us take f of s as a rational function, which is the ratio of two polynomials in S, Ps over Qs. And we know the values of s which make the numerator 0 are called the zeros of this function, and the values of s which make the denominator 0 are called the poles of this rational function. So, let us take the case all poles simple. All poles are simple. In other words, Q of s is the product of some constant k times s minus si, where all si are distinct. That means, if you take I from 1 to n, whatever the factors here, all of them have different values. No two repeat themselves. None of these poles repeats itself. That means, no two si are the same. Now, to handle this, we can write this f of s as k1 upon s minus s1 plus k2 upon s minus s2 down the line kn over s minus sn. If there are n such factors in Q of s, say I from 1 to n, then there are n such factors, and if the numerator degree is the same as the denominator degree, you also have a constant term sub k naught. We will assume in our case that the degree of P of s is not greater than the degree of Q of s, which is usually the case. So, we do not have to worry about cases where you have stop with k naught, you do not have terms like ks squared and so on. So, this is f of s. Now, if this is the partial fraction expansion of f of s, where all poles are simple. So, given P over Qs, we have to put this in this form. If you do that, then we can find out the inverse Laplace transform of each one of these elementary terms quite conveniently. So, that is our first job is to express Ps over Qs to be like this. Now, how do we find the values of k1 to kn? Now, you observe, suppose I multiply all these terms, both this side of the equation and this side of the equation by s minus s1, then I get k1 plus k2 over s minus s2 times s minus s1, etc., plus kn times s minus s1 over s minus sn plus k naught times s minus sn s1 equals Ps over. As far the denominator is concerned, because s minus s1 is the multiplying factor in the numerator, one particular term gets dropped out. So, you have some k, the product of s minus si, I starting from 2 to n only, because s minus s1 got dropped out. Now, if in this put s is equal to s1, suppose I substitute s is equal to s1 in this, then all this will vanish, and on the left hand, on this side you have only k1, and on the other side you have therefore Ps over Qs. What I have really done is we have multiplied this by s minus s1, therefore this s minus s1 got cancelled out in Q of s, and that left this. So, I can put this in this form P s times s minus s 1 by q of s with the substitution s is equal to s 1. So, that is how you can evaluate k 1. In general, any one of these, suppose you want to find k r, all you have to do is P s multiplied by s minus s r divided by q of s. That means, this s minus s r term is cancelled out in q of s. Symbolically, we represent it in this fashion, then substitute s is equal to s. So, that is how you can find out all these factors. These are called the residues of these poles. K 1 is the residue of the pole at s equal to s 1, K 2 is the residue of the pole at s 2, K n is the residue of the pole at s n. So, we can find out all these residues, and once we have all these residues, we can find out the corresponding f of t. So, once we have this f of s, corresponding f of t is easily obtained by finding the inverse transform of each one of these. We recall that k 1 over s minus s 1 has the time corresponds to the time function, which is equal to k 1 e to the power of s 1 t. Similarly, k 2 e to the power of s 2 t, and so on and so forth. One quick example will illustrate this, and then we will be done with that as far as this lecture is concerned. Example: suppose f of s equals 2s plus 3 over s times s plus 1 times s plus 2. So, it has got 3 poles. So, I will have k 1 over s plus k 2 over s plus 1 plus k 3 over s plus 2. So, these are the 3 terms that we have to evaluate. To find out k 1, you multiply this function by s. So, once you multiply this function by s, you have 2s plus 3 over s plus 1 times s plus 2, and substitute the value s equals 0, because the pole is at s is equal to g origin, pole at s equal to 0. This will be 3 upon 2. Now, as far as k 2 is concerned, you multiply this function by s plus 1. So, 2s plus 3 over s times s plus 2, substitute s is equal to minus 1, because s plus 1 must be made equal to 0. So, s is equal to minus 1. If you substitute s is equal to minus 1 in this, you get the answer minus 1. And likewise, k 3, you multiply this by s plus 2. Therefore, you have left with 2s plus 3 divided by s times s plus 1, and you substitute s is equal to minus 2, and the answer for that happens to be minus half. So, the partial fraction expansion of f of s leads to these 3 terms k 1, k 2, k 3, which are evaluated like this. So, from this f of t can be obtained as k 1 by s, 3 by 2 upon s, it corresponds to 3 by 2 u t, plus k 2 upon s plus 1, this corresponds to k 2 e to the power of minus t, k 2 is minus 1, therefore, e to the power of minus t u t. That is the inverse Laplace transform of k 2 upon s plus 1. The inverse Laplace transform of this is k 3 e to the power of minus 2 t, k 3 is minus half. So, minus half e to the power of minus 2 t u t. That is the final result, 3 upon 2 minus e to the power of minus t minus half e to the power of minus t 2 t u t. So, this is how one can find out the partial fraction expansion in the case of simple poles, and from that you can find out the time function to which the original given f of s corresponds to. So, in this lecture we worked out various examples to illustrate the properties of Laplace transforms we had studied earlier, and then we started a discussion on the method of finding out the inverse Laplace transformation of a given function of s, that is to find out, identify f of t to which the given f of s corresponds. And in this direction, we started out with the partial fraction expansion of the given function of time, given function of s, and as a first case we have taken the situation where all poles are distinct and simple, that means no pole is repeated, and we can find out the residues of these poles in a very compact way by multiplying P s upon Q s, the rational function, by s minus S I, where S I is the pole at which you have to find out the residue. So, once these residues are found out, all the k factors are found out, the inverse Laplace transformation is quite straightforward, and that is what we have illustrated by means of an example. We will continue this discussion of finding out the inverse Laplace transformation by partial fraction expansion in the next lecture, where we will consider the situation where some poles are repeated, maybe of order 2 or 3 as the case may be.